you'll excuse me, I'll do this in English. I think that'll work better. I feel like something's come between us, but I'll speak from here. So today is about 2084. What is the future? I want to start by showing you the most important technical forecast in history. In 1954, Gordon Moore plotted 5 data points, which was the number of transistors on early chips. And he noticed if you take the logarithm, they were on a straight line, which means they're doubling. And so he said, what if for 10 years transistors doubled? He wrote an amazing article called Cramming More Components onto Integrated Circuits, where he foresaw the whole digital revolution in 1954. It's an amazing article. He got one thing wrong, which was his forecast for 10 years was actually 50 years. So the data from 1954 for 50 years has been doubling. On a linear graph, it looks like there was a revolution, the digital revolution. But if you take the logarithm, which measures doubling, it's a straight line for 50 years. And so that's called Moore's law, and it gave us digital computing and communication. So what I want to talk about today is this graph. This is one measure of digital fabrication. This is Fab Labs. And they've been doubling for 10 years. So there's more data than Gordon Moore had for a digital revolution in fabrication. And so what I want to do in the next 17 minutes is try to show you the next 50 years of that graph. So data point number 1. Computers controlling machines to make things was invented in 1952 at MIT. And they took the first real-time computer, called the Whirlwind, the first computer that wasn't a batch, that could respond instantly, and connected it to a machine to make things. And there was just one of those. My lab at MIT has the successors, the million-dollar manufacturing machines, to study how digital relates to physical. I had a problem teaching students to learn, so I began a class called How to Make Almost Anything, just for research. But every year, I'm overwhelmed with students who want to come make things. And they make the most amazing things. So on the bottom is a dress with sensors and spines that defends your personal space if somebody comes too close. And then an alarm clock you wrestle with to prove you're awake, or a web browser for parrots, or Kelly, who is a sculptor with no technical background, was frustrated when she wanted to scream and she couldn't, so she made a device to save up her screams. And so it has sensors, electronics, acoustic foams, and so you scream into it, and then it records your scream, and then it releases the scream later when it's convenient to do that. This would go on to show her showing it, but for time I'll go on. And that's when I realized that the students were showing me an answer to a question I didn't ask, which was I was studying how to digitize fabrication, make digital physical, but not why. They were showing me the killer app of digital fabrication is personal fabrication, which is not mass production, it's products for a market of one person. And so in the history of computers, there were about from the mainframes that cost millions of dollars, there were mini computers. And that's what created the internet. And inspired by that analogy, we started setting up what are called Fab Labs, which are mini versions of the big lab I run at MIT. It's about $100,000. It fills about this space. And it lets you make the kind of products you buy, furniture, electronics, boats, bicycles, houses. And an accident happened, which is we opened one lab, then there were 2, then there were 4, then there were 8. They've been doubling every year and a half. There's now over 1,500 of these community labs as a network all over the world for digital fabrication. Once a year, all the labs meet, and I'll tell you more about that. To teach classes like we did at MIT, we started teaching it in the Fab Labs, where students, rather than looking at a screen, have a group of students locally, but we connect them with video. So I'll show you homework. This was one student in a little lab outside Barcelona. He wanted food. So at the beginning, all he knew how to do was make a sketch of an aquaponics system. Then he's learning CAD, and he's designing the aquaponics system. Then he's learning laser cutting to prototype it. Then he's learning large format machining to make the big size version. Then he's doing the instrumentation. Around here, he's learning to design and produce his own electronics. And so if you're familiar with Arduinos, in a minute you'll see his Aquaduino, his electronics to control the food production system. And then he runs the system, and then round about here, I love this picture. Here he is eating his first aquaponic lettuce. It's not a startup, it's not a business. Just using all the tools in a fab lab, he can produce this aquaponic system as a beginner in this rapid prototyping class. So this network meets once a year. We brought the world to France last summer, and it included a really interesting event, a Fab City Summit in Paris. I'll go back to that. This started in Barcelona. Barcelona has a fabulous design sense, but over 50% youth unemployment. A whole generation can't work in a traditional job. And so they started putting these digital fabrication labs in the city as urban infrastructure. And so if you lived in the city, you can produce what you consume. Barcelona's mayor started a 40-year countdown to urban self-sufficiency, a few percent a year. And now many other cities, including Paris, have joined this Fab City commitment of universal access to digital fabrication so consumers can become creators and produce what they consume. So to continue scaling, there's about 1,000 fab labs and there's about 1,000 cities. In the history of computing, what came next were hobbyist computers, and there were about 1 million of those, and that's the number of towns. And so the Altair there, you might not have seen it, but one company started using the Altair called Micro-Soft, and they took the dash out eventually, and it became Microsoft. And another group started using it called the Homebrew Computer Club, and they became Apple. And so these computing pioneers started on these hobbyist computers. And so to do that, what we started looking at was not going to a lab to make things, but using the lab to make things. And so we started studying rapid prototyping of rapid prototyping. And so here's an environment where you design a machine, and it could be big or small, it could have various degrees of freedom. You put the degrees of freedom together, and it makes the parts for the machine. And then this is a really interesting control system where instead of the machine being programmed to do something, it's like a little internet. For the experts, it's a data flow network. So you can make a graph of what you want the machine to do and overlay that on the hardware. And so we were at an arts colony, and this is a clay plotting machine made out of those parts. And so you make a picture of what you want the machine to do, and then you take the parts of the machine and make, in this case, a clay extrusion machine. And the idea is to make it as easy to make the machine as to make the project with the machine, to do rapid prototyping of rapid prototyping. And so that same parts, though, can do many different things. This is a bigger machine for subtractive machining. This is a drawing machine. This is a machine to play a piece of music, Steve Reich's Music for Blocks of Wood. And the machines are as easy to make as the projects with the machine to do rapid prototyping of rapid prototyping. And in fact, with I see Dassault here, we've had a great collaboration with them on these workflows. This is an environment that lets you design in their cloud, and then it interfaces to, the machine is like a little cloud, and so it interfaces their design cloud to this machine cloud to do rapid design all the way through to rapid prototyping in the lab. So to keep scaling, computing went from one mainframe to thousands of mini computers to millions of hobbyist computers. And then it's now in the billion stage. You're all carrying devices you're looking at when computing came universal. And to continue this projection into the future, there's a problem with everything I showed you, which is one of these community labs can make all the things you buy, but there's still a global supply chain to go into the lab. And so, for example, for electronics, the vendor we buy parts from has an inventory of 500,000 resistors, not 500,000 resistors, 500,000 types of resistors, and 500,000 types of capacitors, and 500,000 types of inductors. And you need all of that to create technology. But conceptually, there's just a few properties, like conducting and insulating. And so what I'm showing is pictures of micro Lego. We're making Lego, but that's microscopically small. And then we're making design tools where you place bricks of Lego like a child, but they're functional. They have mechanical and electronic properties. And so here we're designing circuits. And then you take those circuits, and then you put it not to a printer or a cutter, but an assembler. And the assembler takes these building blocks and assembles them into functional systems. And so what this is doing is reducing the huge technical inventory you need to make stuff to this much smaller set of building blocks. And for example, here we're working with Airbus to do this for jumbo jets. Instead of a global supply chain to make the parts for the jumbo jet, you make little parts you can assemble into big high-performance structures that actually work better by doing it that way. So finally, to continue that scaling, computing went from 1 to 1,000 to 1,000,000 to 1,000,000,000. Computing is now going to the trillion stage. And so to understand a trillion, a typical person has about 1,000 things. 1,000 is roughly the number of things around a person. And so if Earth has about 1 billion people, it means, and they each have 1,000 things, there's about 1 trillion things on Earth. And in the era of the Internet of Things, we're approaching 1 trillion devices on the Internet. And so if you look at the Nest thermostat in that picture, the thermostat has the computing power and the connectivity of the first mainframe, and of the mini computer, and of the hobbyist computer. Each of those stages roughly has the capability of one that came before it. But it goes from filling a building to filling a room, to filling a desk, to filling a pocket, to going inside the pocket. And so that's the scaling of 1,000, million, billion, trillion in the history of computing. So now to think about that for going from digital to physical, our inspiration is molecular biology. And so in biology, you're made from an inventory of 20 parts. They're called amino acids, and they work like molecular Lego. What's interesting about amino acids is they're not interesting. They have very simple properties, like they're acids or bases, or they attract water or they repel water. They just have these simple properties. But by assembling them, you can make the motors that are moving me, and the synapses in your brain that are thinking, or the light sensors in your eye. They're all made from these 20 parts. And the way it's done is very different from that inventory I showed you. There's a coding sequence of what you want to make, like a synapse to think. The code doesn't describe a thing. The code becomes the thing. And so that's called primary structure. You turn the code into a chain of amino acids. They then fold into geometrical shapes that just simply are geometry, like helices. Then those make functional units that can do things like add or remove an electron. And then finally, they make machines like the motors and sensors and all of that. So that's how you're constructed. You're constructed out of 20 parts. And most interestingly, the machine that does it is made out of those parts. And so the machine that makes you can make more machines that make more of you. That's the secret of life. And so what we're doing now in the lab is redoing that for technology. And so that's called primary, secondary, tertiary, quaternary structure. And what we're developing is micro building blocks that you can assemble into functions, modules, and systems to make assemblers that can assemble assemblers from the parts they're assembling, self-reproducing systems. And it turns out that's essential for scalability. That's essential to be able to produce the parts. And so this is a really interesting design tool we're developing where you have to design a structure that communicates a computation for its own construction. You have to completely merge communication, computation, and fabrication. It's all digital, but it's digital communication, digital computation merged with digital fabrication to design a self-reproducing system. And these are the sorts of things we're building in the lab today. And so to step back and think about what all that means, this may sound far in the future and abstract, but the pioneers of computing, people like Alan Turing and John von Neumann, they all ended their life studying this question. They all ended their life studying how digital leaves the cloud, leaves virtual, and becomes physical, how computation becomes construction. That was theoretical, and we're at a point now where we can actually do this for real. One way to understand the ultimate implications is I was a science advisor for the movie The Martian, and bonus material for the movie The Martian is how you create civilization on Mars. And at this point in the talk, you should recognize the images behind me. What I'm explaining is you don't go to Mars and redo the Industrial Revolution and figure out an inventory of 500,000 resistors. You essentially create life in non-living material. And we're really asking, what are the minimum building blocks to create a viable technical civilization? Reducing global supply chains, global technology down to the small set of capabilities you can compose to create communication, computation, fabrication. And back to Earth now, where that ultimately leaves is this. The most sensitive, polarizing, difficult issues today all revolve around tariffs. Do you globalize or do you have barriers to trade? Diverging income inequality, jobs, work. Just everywhere in the world, right now, those are the most burning, most sensitive, most difficult issues. If you believe everything I just spoke about, and the reason to believe it is not because I said it, but it's the data. This is all lining up on a scaling curve, like prior revolutions. It has a really dramatic implication, which is for all the attention to inequality and tariffs and all of that, a future is happening, but it's not where people are looking. And the future is, if you can go into a fab lab and make something, then instead of the equality that jobs equals money equals work equals consumption, if you can produce it for yourself, you break that. And so you can produce something for yourself in the lab. You could do it for barter. You could do it for trade. You could do it for money. You could do it for enrichment. You could do it by yourself. You can do it in a small community. You can do it in a collaboration. Just like the history of computing and communication now happens on many scales, it means production and consumption can be much more distributed. And so a colleague in Detroit, which nominally is bankrupt, is creating wonderful labs where a third of the work in the lab is for traditional income, a third is a post-salary economy, it's barter and exchange, and a third is economy but not for money, it's for enrichment and transformation and benefits. Going back to Barcelona, there's lots of press covering Barcelona for Catalan separatism, but what people aren't seeing is neither Madrid nor Brussels really has much to help Barcelona. They're reinventing a new kind of economy where in the city you have access to the means to make. And so in the US, there's a bill for universal access to digital fabrication. In the same way we recognize people need access to the internet, to computing and communication, it's to say that anybody should have access to the means to go from digital to physical and physical to digital. And so stepping back now, just like the last two revolutions, at the very beginning, you can see on a logarithmic plot 50 years of scaling. The same thing's happening now for going from digital to physical. So I've given you a quick portrait of 1,000, million, billion, trillion, and each of those is about 10 years. They all exist today, but they'll take more and more time to come out. But what you should take back from that is you don't need to wait 50 years to do this today. You can already do it with the technology today. It'll get faster, better, cheaper. But it's much more than making something. It's really transforming how society works. If anybody can make anything, how do we live, learn, work, and play? And it really turns on its side all of our assumptions about how an economy and a society makes. And so if you're interested, I invite you to join this revolution that's happening all around you. And in particular, there's a great cluster in France and in Paris doing this. Thank you.